Alright, Logic fans, it's Ash again. We're on our second video on 3.9. This is video 3.9b, and we're learning all about how we can combine CP and IP and nest IP within CP assumptions. And so the last few examples we went over on the last video were basically proving theorems using that kind of technique, but I wanted to show you an example of, you can do this not just for proofs, but for syntactic deductions where you've got some premises involved. So let's assume for the sake of example that 1 and 2 here are premises, and you're supposed to syntactically deduce from that this conclusion. All right, so what I want to do before we even get started on our chart and how to fill it in and everything is I want you to pause and just sort of take a look at the problem. And there's different ways, of course, that you could solve this problem, but we're, of course, going to be nesting CP and IP because that's what we're trying to practice here. But if you were to make an assumption here, what would your assumption be? Okay, and what would you be looking for? Pause now. Okay, so, clearly what you want to be trying to assume here is, hopefully you're recognizing that, well, I've got F as an assumption, right? This conclusion that I'm trying to get here is a conditional, and it's got a structure, whereby F is the antecedent and A and G is the consequent, and so I'm going to be assuming F and looking for A and G. Then the question after that is okay, if I were to make an IP assumption now, right, what would that IP assumption be, and what would you then be looking for? Pause now. Okay, so now, right, you would be looking for, you would be assuming it's not the case that A and G, and you would be looking for anything of the form P and not P. And so doing this kind of scratch work before you start a problem and sort of thinking about how you're going to approach it, okay, is a very useful problem-solving technique and strategy. And, maybe you try to manipulate this guy here into a conditional and make another assumption, right? There's all kinds of things you can do, and there's no right or wrong way to do it, but it is important for you to sort of think about what you're going to try to do. So, given this way of approaching the problem, set up your chart and or your demonstration and see what it looks like, and I'll put mine up in a second. Okay, so I'm sort of experimenting with new ways of presenting this so that you can actually see it, okay? But the idea here is that I've got my two premises lined up, and now I'm going to make an assumption, so I've indented it here. And then we've got our sort of rationales here, and then this is what we're looking for, the conclusion, okay? So one of the things that I like to do even before I start making assumptions is if I want to play with the premises at all, I like to do that before I start making assumptions. And the only reason for that, okay, is that as long as I'm playing with the premises before I start making assumptions, then once I've made the assumptions, what I've played with here will always be available, okay? So it's sort of always going to be there for me, and regardless if I've closed off an assumption or not or discharged it, I can invoke it and it's available to me. But if I play with the premise only after I make an assumption and then I discharge that assumption, then I can't use what I played with. I can always get it again if I have to from the premises, but it's sort of cleaner to approach it this way. So what I'm going to do is immediately just com and simp apart the second premise. And so what I'll end up with is something like this, where all I've done is I've commed and simped apart the second premise, okay? And now what I'm going to do, now that I've got this, and so I know it'll always be available in case I need it, now I'm going to haul off, I'm going to make my assumptions. So as we noted a moment ago, since what we're looking for is this, what we're going to do is we're going to assume this and look for this, and then we're going to make another assumption where we assume the negation of this and look for a contradiction. So straight away it's going to look like this, right? I'm going to assume F, right? And I'm going to be looking for the consequent A and G. Then I'm going to put my IP assumption in there. So I'm going to assume the negation of what I'm now looking for. And I'm going to be looking for a contradiction instead. And so for you, your goal right now is to go ahead and try to combine everything you've got here in such a way that you can find a contradiction, and any contradiction will do. It can be in terms of T, C, A, F, G, something else altogether, okay? So pause now and see if you can find a contradiction. Okay, so there's different things to do here, but one of the things we can do is we know we've got C and we've got G by itself, so this is kind of interesting. And there's a lot of different ways to proceed here, okay? But the way I'm going to do it is this way. And basically what I'm doing is I can't quite see in my mind's eye exactly what the contradiction I'm looking for is going to be. So what I'm going to do is I'm just going to start playing with some of the stuff that I have. I see that I've got F in common here, and so what I'm going to do is I'm going to apply modus ponens, right? And I'm going to obtain this whole thing right here. So this is going to be by modus ponens on, what was that? That was 1 and 6, right? So now I've got that. And again, I'm just looking for a contradiction. So the question is what other kinds of things can I do here? And, you know, again, I'm still not really sure what's going on. There's some pretty advanced ideas involved, but if you don't see anything, just try working with some of the things you have. You know, line 7 looks like De Morgan's could be applied, right? So let's do not A or not G, and that, of course, is De Morgan's on 7. So let's get that down here. And now some things are starting to get a little bit interesting because I've got this G here, right? But then I've got this not G here. And so that should set off a combination possibility for you. Let me make it a little bit more explicit this way. All right, so how did I get that from 9? All right, well, the answer there, of course, is that I used com on 9. And what was the point of using com on 9? How does that help me at all? Well, it helps me a lot because I've got 5 here. So if you can figure out what I'm thinking, go ahead and try to figure it out. But what I'm doing now is I'm basically setting up a disjunctive syllogism. Okay, so that's going to be double negation on 5, which combines 10 and 11 perfectly to yield what by disjunctive syllogism? Not A. All right, and that's disjunctive syllogism on lines 10 and 11. And this is really nice, right? Because now things are really starting to fall into place. I get my not A's here, so I can set up immediately a modus tollens on 8 and 12. And what does modus tollens on 8 and 12 yield? And again, I'm just looking at what they have in common to sort of guide my thinking, right? Well, what they have in common is this, it's not modus tollens, it's modus ponens, pardon me. Modus ponens on 8 and 12 yields C and not T. All right, and now I'm really starting to see how I can get a contradiction. And again, this might not have been the most efficient way, it might not have been the way you did it, but any contradiction will do. But I'm looking at not C and C. So what I'm going to do here is I'm going to go ahead and pull out C, and that's going to be simp on 13. And then, of course, I'm going to build my contradiction outright by just conjoining them together. So C and not C. All right. And again, you could have found a different one. Any contradiction will do, but this is the one we found on this method. And so this is a perfectly fine way to proceed. This was conj on 14 and 4, okay? And now the big payoff question for you, all right? Having obtained a contradiction, which is what we wanted from this particular assumption, all right? What do we do with this particular assumption? Rather, it's this assumption here, okay, 7. So we're going to close that off, right? So in order to close that off, what we're going to do is we're going to go to like where 6 is roughly. We're going to write 16, and we're going to write the first thing we assumed, okay? Then we're going to write arrow, the last thing we got, which in this case is a contradiction of the form C and not C, okay? And so this is kind of nice because that's basically going to be IP 7 through 15. Okay? And that's exactly how that's going to look. And now we're going to follow this up the same way we follow up every single IP demonstration, right? It's going to go LNC, modus tollens, and double negation if necessary, and it will be necessary in this particular case. So let me fill this in for us. And go ahead and just pause now and fill it in for yourself, all right? Hopefully you can see it now. And so here's what I filled in here. Okay, we discharged our assumption that entails a contradiction. We said law of non-contradiction, no contradictions allowed. And that set up our usual modus tollens, which in this case yields this construction. And then taking out the double negations, we end up with A and G, okay? But we still have our initial as yet undischarged assumption. So let's look back at what that was, all right? And it was F, and we were looking for A and G, which handily we actually have here, okay? So we're ready to discharge this assumption that we made back in 6, and so let's go ahead and do that now, and we'll call that line 20, and that's going to be if F, then the last thing we got here, which was A and G in this case, and that's what we were looking for from that assumption, so we're going to go CP 6 through 19, okay? So let me zoom up here so you can see the whole thing again. All right, so 6 was this assumption here, and we were looking for A and G, and we've discharged that now, and this is what we are left with here. If F, then A and G. And if you recall back, that is exactly the conclusion that we were looking for, right? If F, then A and G. And so this is a total demonstration where we had a IP proof embedded inside of a CP proof, and it was fairly involved. Now, you may find faster ways of solving this particular problem. Some of those ways will involve only one CP assumption, one IP assumption, or no assumptions whatsoever, and that's perfectly fine. But take my word for it that there are a great many problems in logic that are far more easier to solve with these techniques than without, so they're very much worthwhile techniques to learn just for efficiency's sake, and just to save yourself headaches. And then historically, these types of techniques play a very important role in philosophy and mathematics and other sciences as well. So keep practicing. Make sure you're doing the problems, okay, in the textbook, and that's the real test as to whether you've got these techniques down or not. Our next video will be moving on to chapter 4, where we're introducing a whole new line of inquiry, where we're going to be looking at quantifiers, and so it's no longer going to be these relatively easy capital A's and F's and G's, but something else entirely altogether. So this concludes our study of propositional logic. So in chapter 1, we looked at how to make constructions like this, how to use our symbols to make constructions. In chapter 2, we looked at those constructions and applied semantic techniques or truth tables to them. And then in this final chapter, chapter 3, we looked at how to apply syntactic rather than semantic truth table techniques to it. We applied the syntactic rules of inference that we've been going over. And both of those techniques will come back later once we learn some more sophisticated ways of symbolizing sentences. All right, logic fans, catch you on the next video for chapter 4.